Hey there, welcome back. My name's Chris, and today I want to continue talking about stepper motors. I've got this stepper motor here, and again, a stepper motor is simply a DC motor that allows you to turn it a specific amount in steps. That's why it's called a stepper. This one is a NEMA 34 size, so it's pretty big, but you can get them in much larger than this and even smaller. So there's one, and this is probably the smallest you can get. So first, let's talk about what we need in order to drive one of these. This motor, again, it's a DC motor, but it requires specific signals to be sent to it in order to operate. That is typically done with a thing called a motor drive or a stepper drive. I've got one here. This one is a GPIO drive, so it is driven from a controller, a microcontroller, or whatever it is that you're running your logic on with GPIO. So just simply high and low signals from a general purpose IO. There are other ones that have an interface like a serial interface, RS-485, even Ethernet, Modbus, lots of different options. Today we're only going to be talking about the GPIO driven steppers. The next thing you also need, let's see if I can get it over here, is a power supply. These motors take a fair bit of power, and generally you have a separate power supply that drives just them. That power supply might also provide the voltage for the logic if you need it. So this motor, I believe, runs on about 48 volts. I'd have to take a look. It's 32 volts. So it runs on 32 volts and about 4 amps for that NEMA 34. But sometimes, yeah, you can see this one, 2.8 amps is what it pulls. That power supply is a 4 amp. The point being that you need a power supply and a drive that match your motor. I'm not going to go into all the details about how to make sure that they all match. The place that I got these, Automation Direct, I'll put a link down below. They have a really good website for being able to select matching components. They also have free help that you can call and talk to a process engineer, and they can make sure that you get what it is that you need and everything is a matching set. Really what I want to talk about is how we actually wire this thing up and drive it. So the first thing we have to do is we need to wire the motor up to this drive. The motor came with, or I purchased a cable that came with it, and so this one specifically is a 4-lead motor. There are also 8-lead motors. So I've got 4 wires here. So if we go ahead and look at the datasheet for this motor itself, I have that here. You can see in this area, it talks about how to connect it. And really what's important here is we've got the red, white, green, and black wires, and they connect to A+, A-, B+, and B-. You can see that these terminals are marked A+, A-, B+, B-, and I've connected the corresponding colors from the data sheet to that. That's all there is to it. Now, if you've got an 8-lead, you can see here's an 8-lead wire. You might have to do this where we've got A+ and A-, so we've got white and green connect to the drive itself, and then you connect the orange and brown together, and then same thing over here. You'd connect the red and black to the B+, B-, and then connect your yellow and blue together. So the next thing we want to talk about is hooking up the control signals. The control signals here go to this PUL+, PUL-, and DIR plus and minus, so pulse and direction. It's worth mentioning that these drives can operate in two modes. One is step direction, and the other is clockwise, counterclockwise. We're going to drive this one with step direction, but we can talk about both. Basically, step direction, the PUL or pulse or step, depends on your drive how they're marked. That step signal is used for telling the motor to do a step, and then the direction signal is in which direction. So maybe direction high is clockwise, low is counterclockwise. And then for each pulse that you give the step signal, it will move one. Now, if you change it to clockwise, counterclockwise, then the pulse will be 4 steps in one direction, and then the direction is 4 steps in the other. So you can pulse one to go clockwise, pulse the other to go counterclockwise. This one supports both. You can see it's got a whole ton of information on here. This will allow you to set which direction it's going, and it looks like on this one, the control mode is switch 14, which is up here. Again, I'm just going to work on step and direction because that's typically the most common way that I'll drive these. There are a whole bunch of other things on here, like the number of pulses per rotation. So by default, this thing does 400 pulses for one full rotation of the motor, which is something like 3/4 of a degree per pulse. But it has a range, can go all the way to 25,600 pulses for a rotation. So for larger, less accurate motion down toward finer, more accurate motion. It's also got some settings for the amount of current that you're going to draw. Current generally equals torque. You want more current is more torque, but it also tends to produce more heat and requires a larger power supply. So wiring this up for pulse direction and really wiring it for the clockwise, counterclockwise, we've got 2 different options. We can connect it either as open collector, so common anode, or PNP, which is common cathode. Really, the idea is you can either provide these signals here with a constant power, you can see here, and then we switch the minus. So we give constant power into the plus versions, and then we switch the minus side to ground to generate signal. The other option is connect all of the minuses to ground, and then we switch the pluses for our signal. In this case, what I've done is I've wired the minuses all together, and then there's a jumper here that comes over to the ground, and this ground goes over to the power supply. We'll talk about the ground here in a minute. There's some important considerations. But the point here is I'm running with this right-hand diagram here where I've connected ground to everything, and then the plus terminals on the drive are what I'm going to be controlling from my microcontroller. For controlling this, I'm actually going to be using a Meadow microcontroller, though for initial testing and for theory of operation, we actually don't even need a microcontroller. We're going to just drive it with stabbing the wires in and out of a power source. Here, I have a couple of basically logic level shifters. There's one on this side and one on this side. I've got a video on how to set this up. I'll put a link up here. The point of this is that the Meadow outputs 3.3 volt logic, and I need 5 volt logic. You can see it says either 5 or 24 volt here. So I need 5 volt logic in order to drive this drive. So I need to convert the 3.3 that comes out of here to 5 volt signals going into the logic on this drive. It's also important So I've got the grounds tied to the ground for the power supply, but the power supply for the motor, that ground also needs to be common with the ground of your microcontroller. So you can see this is the ground from the power supply. It comes over here and it loops in, but then it connects to this black, which comes over to here and eventually routes to the ground on this microcontroller, which is actually the ground on the USB from my PC. Everything needs to have a common ground in the whole system. So I've got a power supply that is driving the motor and a power supply built in here for this controller, which actually goes back to the power supply of my PC on the USB. All of the grounds need to be connected to one another. Otherwise, you have some differentials in voltage and you can get some strange behaviors. So let's go back and look at how this actually operates here. If I move down, they've got a diagram. Here is just an explanation of all the dip switches, same thing that's on the face of that drive. But here is the kind of the meat of how these work. You can see, and it's got some timing diagrams in here, what our minimums should be. These are down in the, greater than 5 microsecond type stuff. So if you've got pulses that are less than 5 microseconds, it's not going to operate. But the general idea here is that the pulse line, we need to pull high, and we pulse it low for every step we want to make. Now, the question is, does it step when we go low, or does it step when we come back to high? Again, because these things are super configurable, there is switch 13 on this, can control which edge that steps on. By default, it by default, it will step on the rising edge. So we start high, we drop it low, and then when it comes back high, it will step one step. The amount of one step is, again, set by how you have the drive configured. So if I just power everything up here, USB, got to go one way, then the other, and then back. And then I bring up the motor. I just put a piece of tape on here as a flag, so it's a lot easier to see when it moves. So now I have the step and direction. I think that's how I have them set up right now. So if I take my direction, which I have connected to yellow, and I pulse the direction, or the pulse line, I guess, you can see it's moving counterclockwise. Generally, you can see that it sometimes goes backward, and that's because there's some bounce of me just stabbing it in there, so it's connecting and disconnecting real quick. And sometimes you can get it where you have two of them in less than that 5 microseconds, and sometimes it will go in the incorrect direction. When we have nice clean square waves from an application driving this, you won't see that. But you can see that it is now going counterclockwise as I stab it in. And then if I move the direction to positive, and I do the same thing, it changes and goes back to clockwise. And right now I have it set at, I think, 400 pulses per rotation so that we can see it. If I set it to, 25,000 pulses per rotation, I'd be sitting here stabbing this in all day in order for you to see it. That's all there is to it. I mean, it's really, really simple. Once you have everything wired up, all we have to do is control that signal. One other thing to keep in mind is the inertia of a motor. The bigger the motor, obviously, the more mass that it has to turn. And when you command it to step, it has to move a full step before you can command it to do a second step. Moving from or going from a dead stop to motion, that takes longer than if it's already moving. So if you're trying to go really fast, you often have to ramp up to the fastest speed. You can't just go from 0 to the fastest speed right away. So that's something to keep in mind. Generally speaking, for what we're going to be talking about and looking at, that's not going to be an issue because I'm just not going to be trying to drive it that fast. And so to show you that other mode, the clockwise counterclockwise mode, we might as well do that while we're in here. I can take, it says here switch 14 is our control mode, so I can take switch 14 and change its mode. And now one line is the clockwise, the other is the counterclockwise. So in this clockwise counterclockwise mode, we pull both of them low so that basically the one that we're not using will be low. And I can take one of them and I can cycle it, pull it high and then low. So again, just like before, and we get clockwise with it. And if I take the other line and pulse on it, I get counterclockwise motion. And really that's it for how stepper motors work. Next, I want to talk about how we can write some code to actually drive these. We'll do some simple code that runs through stepping at, say, 90 degrees from its current location. But then we'll also talk about a driver that I created that's a little bit more complex, that you can tell it where to go, how fast to go to get there, some things like that. But that's it for today. Thanks for watching.